Okay, good evening, all of you, ma.
వచ్చి ఎన్ని చెప్తాను ముతికిచ్చింది అట్ట పెట్టింది ఎటు పెట్టింది అది చేసి గుడ్డు చేసి ఆయన అది పెట్టింది తినేది వచ్చేది మనం అది అర్థం
Okay, the term water potential was proposed by Slater and Taylor. Okay, the term water potential was proposed by Slater and Taylor. The term water potential is used in the place of diffusion pressure deficit. Okay, the term water potential is used in the place of diffusion pressure deficit. Okay, that means the diffusion pressure deficit, or we can use water potential, or we can also use the suction pressure. The suction pressure. Okay, all the three terms meaning the same. There is water potential, diffusion pressure deficit, and suction pressure. Okay, there is, and the difference between free energy of water in a system and free energy of pure water at atmospheric pressure is called water potential. Okay, that means, okay, here why the name given as a diffusion pressure deficit means, okay, how much diffusion pressure that is less than the pure water. Okay, how much the pressure that is a deficit, how much the diffusion pressure that is a deficit to that of pure water, that is determined as the water potential of that particular water. Okay, so that one we call it as the difference between the free energy of water in a system and free energy of pure water at atmospheric pressure is called water potential. So water potential is defined as the chemical potential of water divided by the partial molar water, that is volume of 1 mole of water. It is a measure of free energy associated with water per unit volume. Okay, the free energy. Okay, so that's why the water potential of a water is also described as the chemical potential of water divided by the partial molar water, that is volume of 1 mole of water. Okay, this water potential, how the water potential is designated means, it is designated as the free energy of the water molecules, free energy of the water molecules in a unit volume. Okay, and next, when you observe the water potential is a concept fundamental to understanding water movement. That means if you want to understand the movement of water, we can able to understand the movement of water only when you know what is meant by water potential. Okay, and along with that, we have to know about the solute potential and the pressure potential are the two main components that determine the water potential. So if you want to know the water potential, we have to understand the solute potential and pressure potential, because these are the two components which will determine the water potential of the water. Okay, every molecule when it is in liquid or gaseous condition, it is having certain free energy, and that free energy we call it as, okay, it is in the form of kinetic energy. So water molecules which are in liquid condition, they possess kinetic energy. Okay, in liquid and gaseous form, they are in random motion, that is both rapid and constant. Okay, why this kinetic energy is developed means, because the molecules that are present in the gases or liquids, they are in rapid and a constant movement. That's why they develop, okay, they have got this kinetic energy. Okay, the greater the concentration of water in a system, the greater is its kinetic energy or water potential. Hence, it is obvious that pure water will have the greatest water potential. If two systems containing water are in contact, random movement of water molecules will result in net movement of water molecules from the system with higher energy to one with lower energy. Thus, water will move from the system containing water at higher water potential to the one having low water potential. Okay, if two systems containing water are in contact, the random movement of water molecules will result in net movements of water molecules from the system with the high energy to one with lower energy. So the water will move from the region of higher water potential to one with the lower water potential, because the energy, okay, it is moving from a region of higher energy to one with the lower energy. So this process of movement of substance down a gradient of free energy is called diffusion. So that means here, as the movement of water is taking place along the concentration gradient, that is from higher water potential to the region of lower water potential. That's why we are calling it as a type of diffusion only. So water potential is denoted by a Greek symbol, that is psi, and is expressed in pressure units such as bars or pascals. Okay, by convention, the water potential, by convention, that means it is an assumption. The pure, okay, the water potential of pure water at standard temperatures, which is not under any pressure, is taken to be 0. Okay, that is considered as the highest water potential. If some solute is dissolved in pure water, the solution has fewer free water and the concentration of water decreases, reducing its water potential. Hence, all solutions having lower water potential than pure water. The magnitude of this lowering due to dissolution of the solute is called solute potential or osmotic potential, which is denoted by the letter psi s. Okay, that means the magnitude by which the concentration of what, okay, the concentration of water is decreased by the addition of solute molecule is nothing but called as the solute potential. Okay, which is also called as the osmotic potential, because that only helps in transport of water from one region to another region. Okay, and psi s is always negative, because how much, okay, how much the water potential is reduced, that much equal to the solute potential when a solute is dissolved in pure water. So the value, okay, that means the value of water potential with the dissolving of solute, that one will become negative, because the highest value is 0. When it is decreased, it comes to negative. How much it is decreased, that is equal to the solute potential. So the solute potential is also having the negative symbol only. Okay, the more the solute molecules, the lower is the solute potential. For a solution at atmospheric pressure, the water potential is equal to solute potential. Okay, at atmospheric pressure, the water potential is equal to solute potential. So psi W is equal to psi S. Psi W represents water potential, whereas psi S represents solute potential. Okay, if a pressure greater than atmospheric pressure is applied to pure water or solution, its water potential increases. It is equivalent to pumping water from one place to another. Okay, pressure can build up in a plant system when water enters a plant cell due to diffusion, causing a pressure built up against the cell wall. It makes the cell turgid. This increases the pressure potential. Okay, that is okay. Okay, if a pressure is great, okay, if a pressure greater than atmospheric pressure is applied, okay, the pure, okay, to pure water or a solution, its water potential increase. Okay, which helps in pumping the water from one place to another place. That's why whenever, okay, during a diffusion, okay, by diffusion process only, the water is continuously entering into the cells of the plants. So it is exerting some pressure on the cell wall. Okay, that is called, okay, making the cells turgid. This increases the pressure potential, which helps in driving the water from lower parts to the upper parts of the plant body. Okay, pressure potential is usually positive and operates in plant cells as wall pressure and turgor pressure. Okay, that means, okay, this pressure potential is nothing but the pressure exerted by the water on the walls. That is called wall pressure, or we can also call it as a turgor pressure, because it is keeping the cells turgid. Okay, though in plants, negative potential or tension in the water column in the xylem plays a major role in water transport of a stem. So that means, okay, on the lower side, positive potential is maintained, positive pressure potential is maintained, and in the upper part of the plant, the negative pressure potential is maintained. So because of the difference in these pressure potentials, it is helping in driving the water from the lower part of the plant to the upstream, that is up to the stem. Okay, here the pressure potential is denoted by, they are given like a psi w, but it is psi p. Okay, it is psi p. Okay, okay, it is denoted as psi p. Okay, and next, water potential of a cell is affected by both solute and pressure potential. Okay, by adding the solute, we are changing the water potential of the water, and at the same time, by applying the pressure, we are changing the water potential. Okay, the relationship between them is as follows. At a atmospheric pressure, the water potential of the water is equal to solute potential plus pressure potential. Solute potential plus pressure potential. Okay, here it is given some problems. Movement of water between two adjacent cells. Suppose A and B are two adjacent plants. The osmotic movement of water can occur. Cell A has osmotic potential as a psi s of minus 16 bars and pressure potential of 8 bars. Okay, because the pressure potential is always positive, whereas the, okay, solute potential is always negative. And next, the cell B has osmotic potential of
Sir, can you
minus
say
12.
again, sir?
Okay, the pressure potential is denoted in positive, whereas the solute potential is mentioned, okay, okay, it is denoted in a negative, because the solute potential is, okay, is denoted in negative now, because whatever the magnitude by which the water potential is lowered with the addition of solute molecules, that is called as the solute potential. So, okay, we all know very well the water potential of pure water is 0. When you add the solute, it is decreasing. How much magnitude it is decreasing? solute potential. So it will become more negative. If you add more and more solute, the water potential becomes more negative. As a result, the solute also becomes more negative. But the pressure potential is positive because we are applying some pressure and we are increasing the water potential. So the pressure will be positive for pressure potential, whereas the for solute potential or water potential, it is denoted in a negative. Here the cell A has osmotic potential. Okay, that means the solute potential is of minus 16 bars, whereas the pressure potential is of 8 bars. The cell has a osmotic potential. Okay, cell B. The cell B is having osmotic potential of minus 12 bars and pressure potential of 2 bars. Okay, using the relationship between water potential, pressure potential, and osmosis, that is the suction potential. Okay, identify the direction of movement of water. Okay, that is here. Okay, even though it is having the the lower even though it is having the lower solute potential, but it is having more pressure potential. So always the water will move from the region of a higher pressure potential to the region of a lower pressure potential. Okay, when you observe here, the pressure potential is here 8, whereas in the cell B it is only 2. So which is having higher pressure potential means cell A. So automatically the movement of water will occur from a cell A to cell B. Why? Because here the solute potential is minus 16, okay, whereas the pressure potential is 8. So the net result will be minus 8. Okay, and next when you observe here in the in the cell B, it is minus 12 plus 2. So here the minus 10. So here the resultant will be, okay, that means which is having more potential means okay, minus 8, because the lower the value, the higher the water potential. Okay, the highest, okay, minus 8 means more water potential. Here it is given as the solute potential. Okay, now so minus 8 is the lower value, whereas the minus 10 is, okay, sorry, minus 8 is the higher value, minus 10 is the lower value. So because of this, okay, the water is moving from the cell A to the cell B. Okay, since water moves from higher water potential to lower potential, the flow of water will be from cell A to B. That is minus 8 bar to minus 10 bars. And next, coming to osmosis. The term osmosis was coined by Abbe Nollet in the year 1978. Okay, osmosis is also described as a kind of diffusion, because here also the movement of water into and within plants, it occurs based upon the concentration of water. In plants, it is a diffusion of water from higher concentration to the lower concentration across a semi-permeable or differentially permeable membrane. So in osmosis, what is happening? The movement of water molecules is taking place, okay, from the region of higher concentration to the region of lower concentration, but across a membrane. And next, the diffusion continues across the membrane with an equilibrium is, okay, until a equilibrium is obtained. So till the concentration of both the sides becomes equal, or till the equilibrium attains, the movement of the water will occur. Okay, the net direction and the rate of osmosis depends on pressure and the concentration gradient. Okay, that means the net, okay, that means, okay, in even in the equilibrium also, the movement of the water will occur in between the two sides, which is separated by a membrane. But here the net movement is 0. But Okay, the net movement, the net direction and the rate of osmosis. That means from where to where the finally the water molecules will move depends upon the potential and the concentration gradient of the water. Okay, okay, that's why the osmosis can also be defined as the diffusion of water from its pure state into the solution where the two are separated by a semi-permeable membrane, or it is the diffusion of water or solvent from a dilute solution to the concentrated solution through a semi-permeable membrane. Okay, not okay here. Osmosis is refers to purely to liquids, purely to liquids or solvents. So if you take water here the solvent which will move from the region of higher water potential to the region of lower water potential through a semi-permeable membrane. Otherwise, if water is not there, some other solvent. Okay, here also the solvent will move from the region of lower concentration to the region of higher concentration, because when the concentration of the solute is more means the concentration of the solvent will be less. So always the solvent will move from the region of higher solvent concentration to the region of lower solvent concentration. Okay, a solution which can cause the osmotic entry of water into it is said to be osmotically active solution. That means a solution which will take up water. A solution which will take up water, we are calling it as osmotically active solution. That means a solution with a high concentration of solute. Okay. Here it is given common experiment for demonstrating osmosis is thistle funnel experiment and potato osmoscope. Okay. Thistle funnel experiment. In the experiment, sucrose solution is taken in funnel which is separated from the water through semi-permeable membrane. Water will move into the funnel till the equilibrium is reached. The experiment proves that sugar solution is an osmotically active solution and absorb water when it is separated from the water by a semi-permeable membrane. In the same manner, potato osmoscope also. Experiment useful for demonstrating osmosis by using living tissue is potato osmoscope. When the tuber is placed in water, the cavity in the potato tuber contain a concentrated sugar solution, collects water due to osmosis. The entry of water into the sugar solution proves that sugar solution is osmotically active. The cytoplasm of the cells of the tuber that lie between the sugar solution and the water will act as a semi-permeable membrane, single semi-permeable membrane. And next, types of osmosis. Depending upon the movement of water into and or out of the cell, osmosis is of two types, endosmosis and exosmosis. The osmotic flow of water into the cell when it is placed in solution whose solute concentration is less than that of cell sap is called endosmosis. Okay, that means if the water is entering into the cell when it is placed in a solution whose solute concentration is less than that of cell sap is called endosmosis. Okay, for example, swelling of resins. Okay, resins means dried grapes. When you place the dried grapes in water, after some time we can observe the swelling of these dried grapes. Why? Because the dried grapes, okay, they have lost their their concentration is increased due to the loss of water because of dehydration. So when you place in normal water, As the concentration of resins is more when compared to the outer water, the water will enter into the resin, causing the resins to swell. Swelling of resins when they are placed in water. The osmotic outflow of water from a cell when it is placed in whose solute concentration is more than that of the cell sap is called exosmosis. Okay, if the water is moving out of the cell, okay, when you place the cell in a solution whose concentration is higher than the cell is called as exosmosis. Okay, the same. Shrinkage of grapes when they are placed in concentrated sugar solution. Okay, when you place the grapes in a concentrated sugar solution, the grapes will shrink. And next, when you observe here, okay, we are filtering the water. We are drinking the water, not the drinking water. They say RO, that is reverse osmosis. In osmosis, usually the water will move from the region of higher water potential to the region of lower water potential. Okay, under normal pressure. But here what we are doing means we are increasing the pressure. Okay, we are increasing the pressure potential than the atmospheric pressure. As a result, the water will move from the region of lower water potential to the region of higher water potential. That is in a reverse manner. Okay, that is reverse osmosis is the expulsion of pure water from a solution through a semi-permeable membrane under the influence of external pressure higher than the osmotic potential of a solution. Reverse osmosis is used in removing salts from the saline water as well as extra purification of water. That is, okay, here we can see here. Normally, the water will enter from the beaker into the sugar solution that is present in the thinner through the semi-permeable membrane. But here what we are doing means we are applying some pressure in the opposite direction to prevent the water from the beaker into the sugar solution. That is called as osmotic pressure. Okay, here what we are doing means we are applying more than the osmotic pressure. As a result, the water that is present in the sugar solution will comes out of this big, okay, permeable membrane and enters into the water that is present in the beaker. That means here the process is taking place again is the osmosis. In osmosis, the water will move from the region of higher water potential to the region of lower water potential. But here, the water is moving from the region of lower water potential to the region of higher water potential through a membrane because we are applying some external pressure than the osmotic pressure. As a result, the water is moving in opposite direction. That's why it is called as a reverse osmosis. This is the technique that we are using for purification of water. Salts rich purified water. Okay, and next osmotic pressure. Osmotic pressure. Okay, osmotic pressure was coined by Pfeffer. Pfeffer is the pressure required to prevent the entry of water in a solution. Osmotic pressure is a positive value. Pure solvent has no osmotic pressure. Okay, when solute is added to pure solvent, it develops osmotic pressure. Osmotic pressure and osmotic potential are numerically equal, but osmotic potential has a negative sign. Okay, before we said no, okay? Here, how much pressure we are applying to prevent the entry of water from the beaker into the sugar solution through the membrane that is covering the thistle funnel. That is what we are calling it as osmotic pressure. It depends upon the osmotic potential of the sugar solution. If the concentration of the sugar solution is high, we have to apply more pressure to prevent the entry of water from beaker into the thistle funnel. If the sugar concentration is less in the water that is present in the thistle funnel, we have to apply less pressure. So the osmotic pressure and the osmotic potential are having the same value, but the sign only the opposite. Osmotic potential is having negative sign, whereas the osmotic pressure is having the positive sign. Okay, osmotic pressure can be calculated by osmotic pressure minus okay concentration of water, where C is the molar concentration of the solution, R is a gas constant, and T is absolute temperature. OP minus, okay, osmotic pressure minus CRT. C is the molar concentration of solution, R is gas constant, and T is absolute temperature at Kelvin. Okay, the value of osmotic pressure is related to the number of particles and not molecules. Okay, and next, osmotic depends upon two factors, that is concentration of dissolved solutes in a solution and the pressure difference. Here the pressure means water potential, pressure potential. Okay, and next, what is the significance of osmosis, or where the osmosis is used in the living organisms? Responsible for absorption of water by roots from the soil. Through osmosis only, the water will enter into the roots from the soil, and responsible for cell to cell movement of water through the plant from one cell to another cell. Responsible for turgidity of plant organs. Okay, the turgidity of the plant organ, that means okay, every cell and organ is able to maintain particular shape and size. This is only because of this turgidity, and that is because of the osmosis. Responsible for opening and closing of stomata. And next, responsible for resistance of plant to drought, frost, etc. Okay, that is.